So let's get started. It's a great pleasure to host this early career session, and we have two speakers who will speak for about 25 minutes each. And going first, we have Renyuan from USC, and she will speak on learning in linear quadratic framework from single agent to multi-agent and to mean field. And hopefully you can share your screen. Thanks.
Let me try to do that. Thanks, Ronnie, for the introduction, and thanks for having me here today. It's a great pleasure to present at this seminar series. Let me enter my full screen. So today I'm going to talk about reinforcement learning in the linear quadratic framework, starting from the single agent setting to multi-agent setting, and finally to the mean field setting. This talk is based on several joint works with my wonderful collaborators, Xin from UC Berkeley, Ben and Huining from University of Oxford, and Talia from UT Austin. And Huining is currently a final year PhD student at Oxford, and she's on the job market this year and looking for postdoc positions. So due to the time limit, apologize that I may not have time to discuss the relevant literature in details, but I'm happy to discuss the related references afterwards. And I'll also try to focus on the big picture and high level ideas instead of like bothering you too much with the technical details. Okay, so let me start with the motivation. Reinforcement learning is a popular sub-area of machine learning, and it helps agents to learn to make and improve their decisions by interacting with an possibly unknown environment. So at a discrete time t, an agent takes an action ut at state xt, and then she or he will observe the instantaneous reward r, where the distribution of r may not be available to the agent, and this agent will observe the next state xt plus 1. This is the typical setting of reinforcement learning. So the agent doesn't know the distribution of the reward, and he doesn't know the transition kernel of his state evolution. So this popular scheme of reinforcement learning embraces the big data era, where we have more and more data available for us to help us make decisions. And it also has fewer model assumptions. So this is different from the classical stochastic control theory, where we need to know the full information about the environment in order to solve the optimal policy for to help us make decisions. And possible applications in finance include optimal execution, portfolio optimization, hedging and option pricing, market making, smart order routing, and robot advising. If you're interested in these applications, please check out our very recent survey paper on reinforcement learning in finance. Today, our focus will be mainly focused on this popular reinforcement learning algorithm policy gradient method. This is one of the most popular methods in reinforcement learning because it's very easy to implement, and it's suitable for continuous state control with a wide range of applications, including robotic tasks, video games, autonomous driving, and high-frequency trading. But this is a popular method, but it often lacks theoretical guarantees. For example, whether this method could find the global optimal solution, and what is the convergence rate, how many samples do this algorithm need in order to get a decent result. So those are the theoretical questions we are very interested to answer. Okay, so let me start with a brief introduction of what is policy gradient method. It is an iterative scheme on the policies. For example, if we parameterize our policy by a parameter k, then we can use a first order oracle to update our estimation of this policy by running gradient descent method. So why this is an interesting method? Because it's very easy to implement. We don't need to know anything. We just parameterize our policy and run gradient descent. It doesn't need a lot of knowledge to implement this method, and it's well-developed first order optimization method. It's well studied in this optimization literature, and it can also help us to understand the sample-based and derivative-free version when we don't know the model parameters, where we need to estimate this gradient term with respect to the cost function using samples, which is also relevant in this like literature of model-free reinforcement learning. So for the policy gradient method, the key questions are the following. So when does this policy gradient method on K will converge to the global optimal solution in the single agent setting and to the Nash equilibrium policy in the multi-agent setting and mean field setting? So what are the convergence rate? How should we do the exploration and exploitation trade-off in those settings? So these are very interesting questions we would like to study. And the key challenge comes from the fact that this cost function with respect to case K may not be convex or concave for most of the situations. So this makes the theoretical analysis quite challenging. Okay. So in this talk, we will try to address all these key questions via the linear quadratic framework, because linear quadratic framework is a very well-studied framework in our control literature. We know a lot about these type of problems like the uniqueness, existence, stability, and robustness. We know a lot about this framework. And we know that many stochastic systems are like nearly linear quadratic when they are not. And another reason is that the implementation of this policy gradient method doesn't require the environment to be exactly linear quadratic. And this method shows very promising performance when the systems are beyond linear quadratic. So we think this is a robust algorithm, which is robust to model misspecifications. You may also want to ask, can we apply this method beyond the linear quadratic framework? And I think the answer is yes. So as long as this gradient dominant condition, which I will introduce later, this condition holds, then this policy gradient method should converge. And this condition is also referred to the PL condition in the optimization literature. So for example, in this 2019 paper, they showed that for Markov decision process, if they parameterize the policy with a linear combination of features or with a neural network, this policy gradient method could still converge as long as this gradient dominant condition holds. Okay, so this is first promise of this linear quadratic framework. Okay, so let's talk about how should we set up the framework in the single agent setting and what are the corresponding theoretical guarantee first. Okay, so this is a linear quadratic control problem over a finite time horizon with discrete time scheme. So UT is the continuous control or action at time t from our agent, and xt in dimension RD is the state dynamics at time t. So we see the dynamics is linear in the state and also linear in control. So it's a linear system with a system noise term WT following some like sub-Gaussian distribution. So x0 is the initial state. So this is the cost function that our agent is trying to minimize. We have a quadratic cost function with respect to the state, and we also have a quadratic term with respect to control. Now the question is, how should we learn the optimal policy when the model parameters are unknown, especially in the high dimension? If we don't know A, B, Q, T, and RT, how should we design a scheme to help the agent learn the optimal policy? Okay. So first of all, from the linear quadratic control literature, we actually know a lot of knowledge about this system. We know that under very mild conditions on QT and RT, the optimal solution takes a linear feedback form where this KT star can be solved from Riccati equations. Okay, so this domain knowledge helps us to focus on a smaller class of policies to learn when the agent doesn't know the environment. So in this work, we will focus on the following class of linear policies. So the agent will take a policy which is linear in his current state, and we are trying to learn this matrix KT here. Okay, so in this way, if we restrict ourselves to this linear class of policies, then we can rewrite the cost function as a function of this parameter K. Okay, so we have this function CK. Then now the challenge is, we have several examples showing that CK is non-convex nor non-concave with respect to K. So this is the challenging part when we are trying to design and show the convergence of the algorithms. And so this agent in this system is trying to learn a good policy through this policy gradient step. So in iteration n+1, he updates his policy with the previous policy ktn minus the learning rate eta times the gradient of the cost function here. But when we don't know the model parameters, we won't be able to calculate this gradient term exactly. So what we could do is to access the environment multiple times and try to come up with a good estimation of this gradient term using zeroth order derivative-free estimations. Because every time we take an action, we could access instantaneous reward or the instantaneous cost function in order to approximate this gradient term. So this is the how should we update this parameter when we don't know the model parameters. Okay. So what we showed in this theorem is that if we interact with the system with this amount of samples, m is on the order of log 1/epsilon, then the output policy from the mth iteration will give us a good policy which is epsilon close to the optimal solution. Okay, so this is a global convergence. It doesn't depend on where we start from. It doesn't depend on K0, and it has a linear convergence rate because it's on the order of log 1/epsilon. So the first global convergence of policy gradient methods was first showed in this seminal paper. They developed the theory for infinite time horizon and deterministic dynamics. But we think for many financial applications, we have uncertainty in the state dynamics, and we have a natural terminal time for many financial decision-making problems. So we developed the corresponding theorem for finite time horizon and stochastic dynamics. And the key idea to prove the global convergence is to establish this gradient dominant condition. So for any policy K, if the cost function between the policy K and the cost function of the optimal policy can be bounded by the gradient term, if this condition could be established, then we could use analysis, perturbation analysis, and some concentration inequality to show this linear convergence rate. And the second step is that when we don't know the model parameter, then we need to make sure we have enough sample to have a good estimation of this gradient term and try to bound this with high probability. So these are the key ideas to show this linear, which is the optimal convergence rate in this linear quadratic framework when the agent is trying to update his policy using policy gradient method. So this is the first result we have. And we did this policy gradient method in some real world financial data to try to execute certain amount of shares with all these different stocks. And we can show that our method, we know that financial market is not exactly linear quadratic. So by comparing our result with an explicit solution from Ombrun-Chris framework, we have an average improvement around 20%. So this gives us some confidence that policy gradient method is robust with respect to small nonlinearities in the system, because financial market is not linear quadratic. So this is a small example we have to show the robustness of policy gradient method. Although the development of the theorem relies on the assumption that we have a linear quadratic system, but it performs good on real-world system as well. Okay. So having this foundation and development in the single agent setting, we were wondering how good the performance of policy gradient method in the multi-agent situation would be, and whether this policy gradient method will converge to the Nash equilibrium policy. So this is our next investigation to see the performance of this method for general sum linear quadratic games. Okay. So existing literature in reinforcement learning mainly focused on zero-sum two-player linear quadratic games, and the convergence of this method for general sum linear quadratic games with general n players has identified as an open question in this paper, and they provide several numerical examples to show that for certain situations, it's very difficult for policy gradient method to converge to the equilibrium, even when there are only two players, when they have deterministic dynamics over an infinite time horizon. They provided several examples and intuitions on why it's so difficult for policy gradient method to converge, and it circulate around the equilibrium point without converging to it. And then we realized that with some knowledge from control theory, if we add certain perturbation or noise term in the dynamic, and if we focus on the finite horizon framework, we can actually provide the global convergence guarantee of this policy gradient method for n-player general sum games. And I will talk about the intuition, why stochastic system will help and why finite horizon will help in the setting of learning after I show the main results. So it's a very nice observation. Okay, so the setup of the n-player game is very similar to the single agent setting. We'll have n players. Each player adopts a linear control. So he has a control matrix KTI, which is linear with respect to the state dynamics XT, and this control is in dimension RKI. And all the agents have a joint dynamics XT in dimension RD. So this dynamics is linear in state and linear in agent's control with a noise term here. And each agent has its own cost function CI depending on his own quadratic parameter QTI and RTI. So these model parameters are unknown to the agent. Okay, so we use this K to denote the joint policy of our agents. And for each agent I, Ki is the policy from time 0 to time t-1. So this is the setting. And the goal is to learn the Nash equilibrium policy K star when this system has a unique Nash equilibrium solution and when the agent don't know the model parameters. So this is the goal of this work. So here we assume that agents use a modified version of the policy gradient method to update his policy. So this is a natural policy gradient. After this gradient term, we have a normalization, which is the inverse of the state covariance matrix. So this is a preconditioning. It gives us the steepest descent direction on the statistical manifold. So this is mainly for a technical reason because it's easier for us to carry out the analysis, but we method should also work here. Okay, so now it comes to our key assumption, which is on the system noise. We realize that only if this condition is satisfied, we can show the convergence of the policy gradient. So this sigma x is the minimum of these two terms. The first term is the minimum singular value of the state covariance matrix, and we also have the minimum singular value of the noise term as well. So we need the system to maintain a certain level of noise in order to show the convergence of the result. Okay, so this is the key assumption we need to have for the convergence result. So under mild conditions on model parameters and this key assumption on system noise, we can carry out the global convergence result of the natural policy gradient method. So if we perform the algorithm with n iterations, which is also on the order of log 1 over epsilon, then we can get a policy Km, and Km is epsilon close to the unique Nash equilibrium solution. So the key idea to carry out this analysis is that when we do the perturbation analysis, when we want to compare two different policies, K and K tilde, instead of looking at the cost function between CIK and CIK tilde, we can just look at the perturbation on the individual player I and fix the other agent with the optimal policy. Okay, so this makes the analysis easier, and this analysis is consistent with the definition of epsilon-Nash equilibrium. Okay, and also one of the challenge is that we need to control the impact of other agents when we derive individual gradient dominant condition. We need to make sure that other agents' impact on an individual agent is controllable. And in this case, system noise helps a lot. Okay, so comparing the empirical results in this paper by Mazumdar and his co-authors, where they showed a lot of examples saying that policy gradient method may not work for linear quadratic games, we were wondering why we could be able to show this global convergence result. And here are some thoughts that I would like to share with everyone. So first of all, in this setting, finite time horizon helps a lot, because in the finite time horizon situation, we know that we have a time-dependent control policy. And this time-dependent feedback policy enjoys a self-exploration property, and it ensures that the optimal state and control process could span the entire parameter space. In some sense, it helps to explore unknown situations and helps to explore the environment. Okay, and another observation is that system noise could help because it can smooth out undesired situations, as shown in the paper with deterministic dynamics. Because if the agent stuck in some undesired situation, system noise could help the agents to escape those unpleasant situations. And especially this helps a lot when there are a lot of agents in the system and each individual is facing the competition. And this noise could either come from the original system, and if the original system doesn't maintain a desired level of exploration, then the agents could do some self-exploration. So if the agent adds some Gaussian noise, sub-Gaussian noise in his policy K, then we could also bring some noise into the dynamics to make sure that this criteria is satisfied. So in this sense, we realize that in this n-player game, exploration is important because it can help agents to learn and converge to the Nash equilibrium policy. Okay, so this is the key observations we have from this n-player setting. And we have a qualitative view that, theoretically speaking, exploration is very important for the agents. And we also come back to this example showed by the 2019 paper where they have deterministic dynamics. So we re-implemented their algorithms in the stochastic setting. So on the left-hand side, this is the experiment they have, and we put a very small noise with the variance on around 0.001. So we see that we start with this black square dot and then perform the policy gradient method. And after a lot of iterations, it converged to this final status, which is this green point here. And we see that this is far from the Nash equilibrium policy, which is denoted as this blue star here. And if we add system noise to the level of 0.1, we see that if we run policy gradient method from this starting point, and eventually the agent will converge to a point that is very close to this Nash equilibrium point. So in this example, we also showed that system noise could help the agent to explore and converge to the Nash equilibrium setting in this learning environment.
Renyuan, we have about a couple of minutes left.
Okay, I have I think I have 2 more slides. So in this unclear setting, we noticed that exploration is helpful. How should we quantify this exploration? So we know that if in the objective function, we could add some entropy regularization, then it can encourage individual to do exploration. And there's a very nice paper by Haoran, Renyuan, and Talia. They showed that in this linear quadratic framework, if they add Shannon's entropy, then the optimal policy would be Gaussian. And this is a very tractable and efficient way to do exploration. And this is adapted in practice a lot without much theory established. Okay? So in the multi-population regime, especially when we have a continuum number of agents, we proposed 2 types of entropies to encourage agents to explore. One is the Shannon's entropy to explore self-exploration, and another one is a cross entropy that the agent could adapt to explore other agents' behaviors. So we have 2 types of entropy to explore in the game setting. And what we showed that is in this case, we still have a Gaussian structure for optimal policy, and this is so we know that this lambda term is how much the agent wants to invest in self-exploration, and this lambda CE is how much this agent wants to explore in this in other agents' policy. And in this solution structure, we know that the ratio determines how strong the mean reverting phenomenon is, and I call this a peer pressure, because if you look at other people more than yourself, then you will have a very strong mean reversion. And the total amount of investment you want to do exploration determines the variance of this exploration. And this insight of the explicit solution reduces significantly the complexity to learn, because we only need to focus on this type of solution structure to do the exploration, and this motivates the design of policy gradient method with entropy regularization, which could help improve the stability. I'll skip this picture, which shows the stability when we add entropy, and just stop here. Thanks for listening to my talk. I think
Thanks. Yep. So maybe a quick couple of questions, Arash?
Yes, can you hear me?
Yes.
Okay, thank you so much for the talk. I have a quick question. You assumed in both single agent and multi-agent problem that the assumption was that a unique Nash equilibrium exists, or a unique optimal point exists. Can you relax that assumption? What role does this assumption play in achieving the convergence?
Okay, that's a good question. So here in the control literature, we know certain conditions on the model parameters will guarantee the existence of unique Nash equilibrium. If we don't have unique Nash equilibrium, then this we believe this scheme will converge to the stationary points, so the set of stationary points. So we will have a set of Nash equilibriums, and this policy will lead to the set of these Nash equilibrium policies. Once it reaches to the set, then we won't be able to know what will happen, whether they will stay at one Nash equilibrium or they will jump around equilibrium points.
Okay, great. And we have one question in the Q&A. Let me just read it. It's from Walt. How do you find the parameter A, B, etc., since your method gives policy? How do you do this when you have data and policy only?
Oh, so this policy gradient method is a model-free method. We update the parameter, we update the policy K directly without estimating the model parameters. We don't need to estimating model parameters. We just learn the policy K. Okay, thanks.
Okay, so maybe we should move on in the interest of time. So thank you, Renyuan, for a very interesting talk on everybody's behalf.
I'll stop sharing here.
Okay. And then Philippe. Okay, so next we have Philippe Casgrain, ETH Zurich, and he will be speaking on distribution-free, anytime valid, confidence sequences, and tests for elicitable functionals. Thanks, Philippe.
Thanks, Ronnie. So before I start, I just want to mention that this is joint work with both Martin Larsson from Carnegie Mellon and Johanna Ziegel from University of Bern. This talk is going to be on statistics. So specifically, what we're going to be doing is presenting hypothesis testing and confidence sequence building techniques for elicitable and identifiable functionals. For those who aren't familiar with elicitable and identifiable functionals, these essentially form a very broad class of statistical quantities of interest. In particular, they are quite important in quantitative risk management for their inherent ability to be compared through their scoring properties. But more broadly, this class includes most quantities that people care about in statistics when doing data analysis. Like, for example, this includes quantiles, expectiles, means and variances, regression coefficients, MLEs, and the list of quantities that actually fall into this class is very, very large. And so what we do over the course of the talk is to provide tests that have a bunch of important features. So the first is that they're anytime valid. What this means is that they're designed for a setting in which you receive data sequentially and you allow yourself to retest your hypothesis arbitrarily many times. But I give a precise definition of what this means on the next slide, in fact. The second is that all of this methodology is non-asymptotic and distribution free. So what this means is that we're never actually giving any explicit distributional assumptions and not assuming that we have asymptotic or infinitely many data points. And the last thing is that this methodology actually uses data to further improve the statistical power of tests. So as we receive data, we're actually able to improve how we test confidence intervals to make them even more powerful. So the first thing I'm going to do is describe what sequential testing means. So we're going to assume a setting in which we have a data generating process denoted by X that generates a sequence of data points written as small xi. And the objective is going to be to test a null hypothesis H0 concerning the law generating the data. So in this setting, we assume that the total sample size is unknown and potentially infinite, and the decision to test or to stop data collection can be made at any time and can even be data dependent. And there are actually a large number of settings that actually fall into this testing category. So for example, when estimating the daily P&L of some trading strategy, one might want to continuously retest whether the trading strategy is making money or has P&L exceeding some sort of benchmark. There's also the case of clinical trials in which after a certain batch of people that have been included in the clinical trial, a decision can be made as to whether the clinical trial can continue and whether more patients can be recruited to, further continue the study. So one thing to point out is that standard tests, which are designed for fixed sample sizes, are invalid in this setting. It's well known that if we take a test designed for fixed sample sizes and repeatedly apply a test after multiple data points are collected, this can lead to false conclusions. The main mechanism that causes this is that the type 1 error associated with the test will be inflated beyond the level it's designed for, and you'll be rejecting tests with a probability that's higher than the type 1 error threshold you set yourself. There are methods that exist for correcting for multiple testing, but it's also well known that repeatedly applying these methods will make the power of your test eventually go down to zero. So the main question we try to answer is, how can we construct tests that aren't vulnerable to this sort of p-hacking or this inflation of the type 1 error, but which remain powerful in the long run and work well within the sequential setting? And it turns out that an answer to this question lies in the construction of non-negative supermartingales, an idea which dates back to the 40s, but which has sort of resurfaced in the literature, in the statistics literature at multiple time points. Okay, so now I describe anytime valid tests. These are tests that, as I mentioned, are not vulnerable to this p-hacking within the sequential setting. So recall that we're collecting a stream of data represented by the xi's, and we'll define our filtration generated by the data by ft. and the set tau as the set of F stopping times. Our goal is going to be to reject the null hypothesis if it's false, but to keep the type 1 error bounded by some fixed alpha. So we say that a test is anytime valid at a level alpha if for all stopping times tau, the probability of rejecting the null hypothesis at time tau is always bounded by alpha, assuming that the null hypothesis is true. As I mentioned before, one answer to building such tests lies in the construction of non-negative supermartingales. And the way we arrive at this observation is through a very simple inequality called Ville's inequality. So if V is a non-negative supermartingale with initial value 1, then we have that the probability that this supermartingale ever exceeds a threshold 1 over alpha is always bounded by alpha. So what this allows us to do is very easily construct a test using any process that's guaranteed to be a non-negative supermartingale under the null hypothesis. The way we construct this test is, given this process Vt, our test will reject the null hypothesis at time t if ever the process exceeds this threshold 1 over alpha. And by Ville's inequality, we know that this test is guaranteed to be anytime valid. There are a number of, it's actually under many standard hypotheses. These sorts of processes are quite easy to come up with, and I just provide 2 examples here. So for example, in the case where we're testing whether data is IID Gaussian, the following processes, which are form a family of non-negative supermartingales under the null. Very similarly, the classic likelihood ratio will also form a family of test martingales for all indexed by all, I guess in this case, Markov kernels that dominate the kernel in our null hypothesis. So another important observation is that given a family of test supermartingales indexed by maybe some finite dimensional index set lambda, it's possible to combine elements of this family using mixing. So to be specific, if we have a sequence of f predictable measures pi on our index set lambda, then using the construction that I list here, which essentially mixes these test supermartingales at every single time point, we can guarantee that this process is also going to be a valid test supermartingale for the null hypothesis H0. So the idea is that by perhaps combining a base class of tests, it might be possible to create tests that are still anytime valid, but that potentially have a higher amount of power than any one individual test within this class. And there's also a very nice trading analogy that comes into play here. So if we think of the base class of tests as a collection of assets generating returns Ri, denoted by this equation here on the right, and we interpret the sequence of measures pi as portfolio weights, then using the definition above, or essentially rewriting this mixing construction that I wrote on the previous slide, we find that the composite test supermartingale can be interpreted as a wealth process, which corresponds to the wealth accumulated by using this sort of trading strategy given by the sequence of measures pi t. So how we interpret this is as follows. If the null hypothesis is false, then you could potentially make money by betting against the null. If the null hypothesis is true, it's unlikely we'll ever make money because by Ville's inequality, the probability of this wealth process ever exceeding a threshold 1 over alpha is always bounded. But if the null is false, it might be possible to make enough money to reject our null hypothesis, which would correspond to our wealth exceeding this threshold 1 over alpha. And so this idea has been used specifically, or the idea of using smart trading strategies to combine tests has been used specifically for testing, for hypotheses which test means of bounded random variables. What we do here is we extend this framework to a very broad class of functionals or of statistical quantities, which are elicitable and identifiable functionals, which I define and explain in the following slides. So we say that a functional T mapping the space of measures into some set lambda is elicitable if there exists a score function S such that the functional is the minimizer of the expected score. All this is saying is that our functional is elicitable if it minimizes some loss function in expectation. There's a related notion of identifiability, in which a functional is identifiable if there exists an identification function M such that the functional is the root of the expected identification function. We can think of the relation as follows. If S is a convex score, then the associated identification function will simply be will simply be the gradient of the score function itself. One remark for folks that actually work in this field, the definition that we present here includes higher order elicitability and identifiability, which allows for multivariate functionals, which typically they're kind of set apart, these definitions, but here we all lump them up into one. Oh, as I mentioned, this class of functionals is really large. So for example, this includes the mean, the quantile, regression coefficients. It includes maximum likelihood estimators, method of moments estimators, M estimators, Z estimators. The list is very, very large. Okay, so what we're interested in is testing hypotheses of the following form, that our functional is equal to some constant lambda 0. In the elicitable case, we write it out this way. We say that our null hypothesis is the set of measures for which lambda 0 is the expected minimizer of the score function conditional on our the filtration generated by our data, sorry. We write here the conditional expectation simply because it's a generalization of maybe the simpler IID case. This allows for perhaps time series data that has some sort of dependence within it. Similarly, in the identifiable case, the null hypothesis can be written out similarly. So in order to actually build tests for these, we're going to need to make some assumption on data. It's actually impossible without any additional assumption to build tests that have power. So what we assume is one of the following two things. So either we assume that the absolute difference in the score function or the norm of the identification function are uniformly bounded. This allows us to get some results, but the assumption that these are uniformly bounded is somewhat strong. So we also look at the second case in which these quantities are sub C. The sub C assumption I'll define further on, but this is essentially a bound on the decay of the tails of the data generating distribution. And this will allow us also to build a family of tests that works. Okay, so what we're going to do is we're going to try to build families of tests for the four cases I mentioned. We either have an elicitable or identifiable hypothesis, where we assume that the data is either bounded or sub C. And then the second part is going to be to construct smart betting strategies and create portfolios of tests that actually give us high power. So in the bounded and elicitable case, we're able to easily construct a family of test supermartingales constructed as follows. So if our data is bounded, this is a valid test supermartingale for any index by lambda. In the bounded and identifiable case, we similarly can come up with a family of test martingales, which are indexed by vectors within the ball of radius 1. Okay, in order to move to the unbounded case, we have to present the sub C property. I'll go over this quickly for the sake of time, but the idea is as follows. A family of random processes is sub C if there exists a function psi such that the conditional moment generating function for the centered process is bounded by e to the psi. The requirement is that the function psi itself resembles a cumulant generating function, which is essentially amounts to these three conditions here. This can be interpreted as something like a bound on the decay of the tails of the distribution. And this is easily seen by Chernoff's inequality, in which you see that the sub-C condition implies exactly a bound in terms of the convex conjugate of the function psi. This is also a generalization of the commonly used definitions of a sub-Gaussian random variable, sub-Poisson, sub-exponential, and so on. And a last thing to note is that all bounded random variables are automatically sub-C, which follows by Hufting's lemma. Okay, so in this case, we can also easily construct parametrized families of test supermartingales using essentially the sub-C property, which are highlighted in orange or in blue over here. So in all four cases that I mentioned, we were able to construct families of tests. The next task will be to try to find ways to optimize and to combine families of tests in order to create more powerful ones. So the idea is that we want a powerful test. What this means is we want the probability of rejecting the null hypothesis when the null hypothesis is false to be large. So given this portfolio construction, we essentially want to come up with a set of strategies that makes the portfolio value grow large whenever the null hypothesis is false. So one thing we do to simplify our the problem for ourselves and to make it more computationally tractable is that we restrict ourselves to strategies which are Dirac functions. So essentially our portfolio our portfolio strategy at each time point selects a single asset to invest all of its money in. The main idea is that this makes it makes it easy to optimize things using gradient descent or optimization techniques, which we'll do eventually. So for strategies of this type, the most natural benchmark to use is the regret. What the regret is the maximum, the highest retrospective log, or how do I say? It's the largest value of any single test I could have chosen minus the log value of my portfolio process. So if we have a strategy that works very well, we'd expect our regret to grow slowly. Essentially, if we're able to beat this benchmark of the best retrospectively chosen test, then we'd be doing well with our trading or portfolio allocation strategy. So the task of minimizing our regret in the long run without any other assumptions on data is actually a generic online learning problem. And the advantage to this is that there are a number of simple algorithms that are known to work well in this setting. So some simple ones include follow the leader, which simply at each time point picks the best performing test up until that point. There's follow the regularized leader, which does this with some sort of regularization terms. There's online gradient descent, which is sort of related to these two and optimizes by just incrementally, changing the best test that it actually wants to allocate to. And under a number of assumptions, it's possible to guarantee that the regret will be bounded and sublinear. What this means is that on average, as t grows large, we'll be performing as well as the best retrospectively chosen test. So now comes, I guess, an important result. So if we use any sequence theta t of asset choices with sublinear regret, and there exists a theta prime, so a single asset within our family that is able to reject the null almost surely, then in the limit, we have asymptotic power 1. So this essentially implies that whenever somewhat weak conditions are met, we're able to we can guarantee that any strategy with sublinear regret will eventually reject the null if it's false. Although this assumption here might appear difficult to check, it's actually we can show that it holds very often in a lot of simple cases. For example, in the IID case, this condition is met whenever the null hypothesis is false. It also translates to very simple conditions whenever the data generating processes are Gaudic as well. So another extension to this method is to build anytime valid confidence sequences. So these are simply, I guess, the confidence set analog to the anytime valid testing framework that I presented early on in this presentation. So anytime valid confidence sequence is simply a set of sets, CT, such that for all stopping times tau, the probability of the functional falling inside of this set is always at least 1 minus alpha. And it turns out that it's quite easy to construct these sets using the testing methodology that I presented over the previous slides. Essentially what we do is we say that our confidence set at time period t is the set of all lambda 0 that have not yet been rejected by our tests. So essentially all we do is we create portfolio processes for each potential lambda 0, and we just track which ones have been rejected or not. Okay, so just to wrap up, I'll present a few simple examples in which we just apply this methodology to show that it works. So one easy one is when we have a data generating process with AR1 dynamics. So we assume that there's some unknown beta, an unknown parameter beta, which is driving the dynamics of the data generating process. And we have noise here, which is assumed to be sub-exponential. So it's a sub-exponential martingale difference sequence. We don't actually assume anymore. This is just saying that the tails of our data decays at least exponentially. Or sorry, the tails of the noise decay at least exponentially and are conditionally centered random variables. So we're interested in testing hypotheses about the value of this beta. So in our case, we can test something like the hypothesis that beta is equal to 0.75, and we could simulate, with some sort of simulated process to see if this method actually works. And we could see that, at least in this example, after 100 data points, we're already able to reject because we're able to bring our portfolio process over the threshold of 1 over alpha. Similarly, we can construct our sequence of confidence intervals, which we can simply track over time. And we plotted here compared with the best estimate of beta up until this point. So similarly, you can look at IID data. So you can think of, xi is generated by some beta random variable, and you can test hypotheses on the var and cvar simultaneously. So we can say something like our hypothesis is that the var and cvar are both equal to 0.3. And under this data generating process, we're also able to correctly reject the hypothesis after a certain time, and we can create these confidence sequences in a very similar way. So just to conclude, over the course of the talk, we were able to build powerful and easy to use tests and confidence intervals for a large class of statistics that are distribution free, anytime valid, which are data-driven and dynamically optimized, and have asymptotic power 1 under light conditions. So that's all for my talk. Thanks for listening.
Thanks, Philippe. We have a couple of minutes for questions. Arash again.
Hi, can you hear me?
I can hear you.
Yes.
Okay, so my first question is about the theorem that you had. If there is a parameter that from the alternative set that rejects that has like that log goes to in limit that log goes to infinity,
Yeah.
then Q almost surely, and Q is the set of all alternative measures, right?
Sorry, so this is so this is for any measure Q, if this exists, if this is true. So okay. Actually, if Q is not in the null, or how do I say, if Q is not in the null, then in a lot of simple cases we can show that this is just true anyways. Okay, I didn't see that log. That was basically what I didn't understand. Thank you. Another question that I have is about when you actually
create a martingale. I see some of the applications that it's kind of intuitive to see what the martingale is. It's inherited. But for example, for var and cvar, I cannot see what the super martingale that you make is.
Yeah, so it's also for the sake of time, but I mean, our preprint isn't out yet, sadly, but I mean, this is covered there. In fact, if you want to look up specifically var and cvar, how the score functions are built, if you have the score function or the identification function, then it's easy, you know, using one of these constructions to build the test. But for this, I recommend looking up these authors here, or look up elicitation of var and cvar, and you'll find.
And so this construction also makes it clear why it is model free. Is that right?
I mean, it's model free because all you need is a score. I mean, no matter the distribution, it's going to be how do I say, these quantities will be elicited by those functions regardless of the underlying distribution.
Okay, awesome. Thanks so much.
Great. Other questions?
There's a comment in the chat there or a question.
Okay.
Thanks, Sam.
I don't see it. Oh yeah, Sam, do you want to say it?
I was just going to comment. I thought that cvar was by itself not elicitable.
Yes, so that's
you
why
have to have the bivariate elicitation.
Yeah, it needs to be done jointly with the var, which is in the example I provided, can be done, though hypotheses can still be tested individually on them. I actually removed this also for the sake of time, but we also consider testing set value hypotheses. Testing a single one of these quantities it essentially boils down to testing, I guess, to testing a set valued hypothesis, and it's possible to test only one of them. Though implicitly, you require the computation of both of these tests underneath the hood. That makes sense.
So does that mean that as you expand the number of items, the power of the test collapses, as usually happens in high dimension?
The power would actually increase because there's another dimension along which you can reject, if that makes sense.
No. Because normally you need the confidence bounds to get bigger as you add dimensions.
Yeah.
In order to be valid confidence regions for the whole vector.
Maybe if we went to the actual graph, we can maybe make sense of this a little bit better. Can you repeat that last comment?
So if I'm just thinking about adding, there's this weird phenomenon that if I'm just estimating means from simple data, then if I add a whole lot of noise directions and look at a confidence region for all dimensions at once, my confidence ellipse gets very, very big in any individual dimension.
Yeah, okay.
And so my question was, if I have to add dimensions in order to get elicitability, does that mean that everything ends up degenerating due to that addition of dimensions?
Exactly. So in this case, you would have to run this same test on both the var and cvar, but you'd reject, essentially your rejection set would consist of a line in here. So if ever the cvar does not intersect that specific line, I guess it would actually be in the horizontal axis here, then you would reject, if that makes sense.
Okay, so you can build the univariate rejection sets even though you're in a higher dimensional space.
Yeah, you kind of have to like do it in the high dimensional space, but then the procedure is, I don't know how to say, it's like only if this entire set is no longer intersecting with your confidence.
Okay, thanks.
Okay, great. So that we're right on time. So let me stop the formal part here and thank Philippe for your talk.